Hey everyone, Mr. Skelton here. We are back at it. We are continuing on in Unit 8, and today we're going to start Lesson 5, Geometric Series. Just to kind of give you a quick review of what we've done in the past, we started off Lesson 1 with arithmetic sequences, and then we went to Lesson 2, which was geometric sequences, and then we went 3 was arithmetic series, okay, and then we snuck in number 4. Number 4 is just a notation, right? Summation notation. It's how we write something. And so you're going to see that carry over today in 5, which is geometric series. So it kind of goes, if you're looking at the big picture here, we have arithmetic sequence, geometric sequence, arithmetic series, geometric series. We sneak in Unit 4 there just so that we can use the notation of summation notation to write things out, just to show things a little bit differently. So you're going to see a lot of things that carry over from the geometric sequence, Lesson 2, into the geometric series. Just like when we did Unit 3, which is arithmetic series, we had to recall some information from arithmetic sequences. Okay? Learning target there you can read, so you can take a second and take a peek at that. And let's just jump right into it. So today our focus again is on the geometric series. Found my highlighter here. What is it? It's finding the sum. Remember that series is sum, finding the sum of a finite, which means it ends, this series ends. If you look at this first example here, the last term is 524,288. It's not infinite. Infinite means it goes on forever. So we're talking about a finite sum in a geometric sequence. Now, in all the other lessons up to this point, we have developed the formula to so that you can have an idea of how this formula comes into play. For this one, it's a little lengthy, and I don't want to do it in the notes just because it's going to take a lot of time. But this is the formula for a geometric series. This is what you're going to be using. Okay, and we'll talk about it, but this is what you're going to need to know. So here's an example. This is a sequence right here. Remember, if it's a series, that we're going to be adding those things. So if you wanted to write it, it would be 1 plus 2 plus 4 plus 8 plus 16, right? Dot, 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 etc. That is a series. A series is when you add them. Now, we would still be wanting to find the common ratio, and we're actually going to do this problem on the back, but we just want to talk about the formula here since we're not developing it. What do you need in order to find the sum? Well, let's take a look at the formula for that. We would need to know a sub 1, which is nice. We know that for this example it would be a 1. This 1 is always going to be a 1. It never changes as part of the formula. Minus r. Remember, r is the common ratio, and that is what you are multiplying every term by to get the next term. Okay? That's the common ratio. N is the number of times. Basically, this n represents the upper limit. Okay? That's your upper limit. That's how many terms are in the total, the highest number of terms in the sequence. And then obviously this 1 is always going to stay a 1. And this r is always going to be your common ratio again. So this r and this r, it's the same exact number. Okay? So what would we need in order to find the sum for this specific geometric sequence or series? We would need to know what term number this last number is. We already have the 1, and we got to find the common ratio. Okay? Let's flip it over and do that problem here. So if we are looking at, oops, let me lower this so you can actually see it. I'm going to put that formula again. I'm going to write it right at the top so you can still see it. And it's a sub 1, 1 minus the ratio upper limit over 1 minus r. Okay, so we already know, again, if we were to fill this in a little bit, we already know that the first term is a 1. 1 minus, now what's the common ratio? What are we multiplying every term by? It looks like we're multiplying everything by 2, right? Times by 2, times by 2, etc., etc. So my r is 2. Now, we got to figure out n. What is the upper limit? Or what is the last term number here for this? This is term 1, 2, 3, 4, 5, etc. We want to find out what this is. So we have to go back to our explicit formula for a geometric sequence, right? So 524,288 is, where did we start? It's the first term, a1, which is 1, times my common ratio, which is 2, to the n minus 1 power. Okay? And that is your formula for explicit formula back in Unit 2. So 524 288 equals 1 times 2 to the n minus 1, and that's what we want to solve for. So I would divide both sides by 1, but anything divided by 1 is itself. So basically I have 524,288 equals 2n minus 1. So I got to log both sides. So log base 2 both sides. Okay, so you got to take out the old calculator. Whoa! Take out the old calculator, use change base. So this is, remember, this is going to make 1, so I'm just going to be left with n equals 1 on the right side. So log of 524,288 divided by log of 2 equals, and I get 19. And then I'm going to add 1 to both sides, so n equals 20. That's important because now I know that this is the 20th term in this sequence / series. Okay? So when I go back up to my formula, I'm going to put my 20 there, because again that's the upper limit, and then it's divided by 1 minus 2. Now, how do you find this sum in your calculator? Well, what we can also do, what I'm going to do is put it in summation notation for you here so you can get used to this. Remember, that's the upper limit. We're starting with the first term, and then we write the explicit formula, right here, if we're putting that thing into summation notation, which would be just, let's see, it's going to be, where was it at? 1 times 2 to the n minus 1. That would be summation notation right there. Okay? All good? All good. So let's find the actual sum. So when we're putting this in our calculator, we have to do what's inside parentheses first, and we have exponents. So this is going to be 2 raised to the 20th power, hit equals. We're going to have 1 minus second answer, hit equals. We're going to times that by 1. So times that by 1, obviously be the same. And then we're going to divide it by a negative 1. So my sum for this is going to be 1048575123123. So my sum is going to give me 1,048,575. Okay? Nice. Next question. How many Homestead High School graduates will there be in 2018, assuming a 6% increase in graduation rate every year? So I'm kind of giving you a heads up here. Now this is a little tricky because you have years here, and we got to figure out term numbers, right? Like this is the 20th term. We're used to having numbers up here, and now we got years, so you got to do a little bit of thinking. Now, I told you that it's an increase of 6% each year, so what are you multiplying each term by? You're multiplying by 1.06, right? So that's going to be your R. Now, in 2018, we're starting in this is the year actually Homestead started, was 1978, and there was only 65 kids in their senior graduating class. This is kind of accurate. Well, it's 2018 right now, right? So it's 2018. Let's see, if 1978, you add 22 to that, that gets you to the year 2000. So you're at year 2000, that's 22 years to 2018. So that's going to be 40 years. Okay, so 40 years is going to be my term number. It's going to be 40 years since 1978 is what we're trying to figure out. So when we go to do our sum, okay, it's going to be your first term. Your first term is 65 students, so your A sub 1, pull down here, your A sub 1 is going to be 65. 1 minus the common ratio of 1.06, and we're raising it to the 40th power, right? Because I have had 40 years, or so there's 40 terms in this sequence, in this series, excuse me, over 1 minus 1.06. Okay? And again, a lot of this is just calculator work. So 1.06 raised to the 40th power, hit equals. And then I'm going to go 1 minus second answer, hit equals. Okay? And then I'm going to times that by 65, hit equals. And then I'm going to divide that by, in parentheses, 1 minus 1.06, hit equals. And I'm going to have the sum of 10059. We're not going to round up, right? So that seems a little bit big there, but the sum of that, that's how many high school graduates there were since since 1978. If you add up all the graduates, that's not in the year 2000. That's not how many graduates we're going to have in 2018. That's just how many we're going to have total over the course of the year. So if you add up the 65 seniors, the 69 seniors, the 73 seniors, so on and so forth, all the way to 2018, there's going to be there's been over 10,000 graduates at Homestead High School since 1978. Kind of neat to figure that out, okay? I could ask you how many students there will be in 2018. You could figure that out. That's rear view from 2. Last question here. You are an accountant because you love crunching numbers all day. All day, little Nelly reference there. You guys are probably rolling your eyes. Okay. Your starting salary is $36,200. Every year you will earn 4% raise. How much money will you have accumulated in 40 years? Not how much will you have in the 40th year. How much will you have accumulated? That means the sum. So you got to look for those key words. Just like this question here with the graduates. I'm not asking you for. Actually, I did. I said how many high school graduates are there in 2018? I shouldn't have phrased it that way. I should have said total students through 2018 because that's a little misleading. I wanted the sum there. Okay, so I apologize for that. I want you to hit pause and try this on your own, see what you come up with. Okay, so basically we're starting out at $36,200, okay? And we know we're getting a 4% raise, so I'm going to times this by 1.04. So if I take 36200 times it by 1.04, okay, I'm going to have 37648, and we could keep going, so on and so forth, right? Some students like to write out. That's fine. We don't have to, okay? Let's see, before we find the sum, I know I didn't ask you to do this before I asked you to hit pause. See if you can write this in summation notation. Can you write this in summation notation? Okay. Well, how much money, what's your upper limit? How much money will have accumulated in 40 years? So we know we're going to have 40 terms because we have 40 years worth of salary. And we want to add all those up, starting first year. And then what goes here? Remember, this is the explicit formula. This is the explicit formula for geometric sequence. Well, what's that going to be? So really we're going to have 40 n equals 1. The explicit formula is the first term, so 36,200 times the common ratio 1.04 to the n minus 1 power. If I ask you for summation notation of this problem, this is what it would be. Now, if you put a 39 here, I would still accept that. Okay? So let's go ahead and find the sum. Let's write our sum formula down. So I have S sub n. My first term is 36200 times by 1 minus the common ratio 1.04 to the 40th power, because again there's 40 terms there that we're going to be adding up, and divided by 1 minus 1.04. Okay? So let's take our calculator. Again, calculator is important. Make sure you're doing things in the right order. 1 minus the second answer. We're going to times that by 36200. We're going to divide that by 1 minus 1.04. And I should get 3439923.66. So 123, 123. So you've made almost $3.5 million. $3,439,923.66. Not a bad 40-year career. Okay, so that's all the examples I have for geometric series. Also added some summation notation in there for geometric series as well. But like I said, should be in good shape. I look forward to answering any questions you may have. I apologize again for the wording on the graduates program. I wasn't specific. When you read this, it looks like I'm asking exactly for 2018, but I wanted the sum. I will be more, the questions you'll see will be more specific, so I do apologize for that. This is a better question here, accumulated in 40 years, keyword there, accumulating. So you do have to pay attention to the wording. And again, if you have any questions on anything, look forward to helping you in class. Take care.